Alright, hello everyone. Today is Saturday, June 14th. It is the day before Father's Day. I kind of want to make this quick because I plan on preparing some food for tomorrow for Father's Day. I was out all day for one of my little cousin's birthday. So today, or tonight, I'm going to finish up some problems, and then I'm probably going to start preparing for food for tomorrow. But for the problems today, we have binary search. Looks like if we can make good time today, we can see if we can finish off binary search as a whole. I'm not gonna lie, I have been hating binary search, which is surprising because I actually really liked the algorithm by itself, but in the context of the situation, I think it's just not fun at all. It's really challenging, which is interesting. Okie dokie. So problem 981, time-based key value store. So I need to design a time-based key value data structure that can store multiple values for the same key. Oh, dude, I hate design problems. Oh my days. I can store multiple values for the same key at different timestamps to retrieve the key's values at certain timestamps. Implement the timeout class. This is binary search? Returns a value such that set was called. Huh? Okay, so the greatest value that's less than the timestamp we give it. Okay. Sure. So we'll do a hash map for our key. Just for the key. And then for the value, it'll be an array of tuples. Does the time always go up as I'm setting, or can it be going down? Time's always going up, then we're good. But if it's not, then it has to be inserted properly. Haha! Yes, beautiful! Thank the Lord. Okay, and this could be not horrifically hard. Okay, so what I'm doing here is I'm basically initializing everything inside to hold the timestamp and the value. So that is the easy part. The hard part is getting it. So this we want to use binary search to grab the value depending on the time we're given. So I'm going to say array equals, or if key not in self.hash map turn back. The interesting part about this problem is it's like we are not necessarily looking for a value per se. We're looking for the maximus value potentially. So we'll say Maximus time is equal to 0 to start off with, right? Something like that, Maximus time. And num2 will be an array, so I can edit it. While left pointer is less than or equal to right pointer, middle pointer is equal to left pointer plus right, right pointer minus left, right pointer minus left pointer divided by 2. Okay, so then I'm going to say if middle pointer is, if array of middle pointer zero is equal to timestamp, then we can simply do a return statement here. I'm writing too many return statements. This is kind of archaic. But we can write return return the value. So we're getting the Maximus value. What's up, big guy? Elif, if the alright, hold on, Max, relax. The array of middle pointer of 0 is less than timestamp. Then we're going to we're gonna move, say, a left pointer. We need to move to the right. So, hi, big guy. The cat is on the armrest of my chair, sniffing the mic right now. Alright, dude, I understand. No longer protected. Left pointer is gonna be equal to middle pointer plus 1. Oh, he's rubbing his chin on the mic. I hope y'all heard that. And then I'm going to say Maximus time. What's up? Yeah. How you feeling? Feeling like a baby? I'm going to say Maximus time. Alright, hey, I'm here for you, okay? So if maximus time of 0 is less than or equal to, what should be okay? Honestly, maximus time should always like kind of grow with this. I don't even think I need to do Nifty here. I could probably just grow it because I think, right? Based off of the problem statement. We'll see. Moving to the left, then you know, don't really need to store anything. And then I'm just gonna do turn maximus time 1. Yeah. Let's try that out. It's probably not gonna work, but let's see it. Ooh. Hazmat. Yeah, what's up, big guy? I wonder how many spelling mistakes I made. Probably 400,000. Alright, well that passed. Well, that one wasn't too bad. I know how to make this cleaner, but I'm not going to, because I'm lazy. What I would do, pretty much, is just get rid of all this return statement and just drop it down here and say, if it's none, then we're done. You know? Median of 2 sorted arrays. I feel like I've done a problem like this before, like in my algorithms class. Feels like this sounds familiar. Oh. Oops. Sorry about that. So giving 2 sorted arrays. Nums 1, nums 2. Size m and intersect return the median of the 2. Oh my goodness, I have done this one. Dude, I think I hated this. I think I remember hating the hell out of this one. I fondly remember trying this. I don't remember like how I came to my solution or anything like that. I just remember banging my head against the wall because it sounds easy, but when you start working on it, I remember it was a pain. Let me think. Oh yeah, right. That's so silly. I mean, oh no, right. So I was like, we could just merge the array and then run it, but no, that's not log of n plus n. That's it. That's just O of n plus n. Because that'll be a linear pass. The median. This one has a very particular way of solving it. I think it's like your first thought is like you want to I'm thinking my first thought is like I will do the median here, and then I'll like kind of compare them. I think like if they're the same, then I can be kind of confident that we're in the same ballpark. Oh, days. Okay, so this is actually a hard problem. You should, oh wow, aim for solution of the minimum. Really? So this one says otherwise. Here he's saying we can do better. We can just get the minimum. 5 hence. A brute force solution would be to create a new array. Think of a better way. Maybe you can use the criteria of both the arrays being sorted in this ascending order. I mean, right. Sorry about that. I have an idea, just like a bare idea, but I mean I don't know if this idea would work. But let's see. If I did, so the median here is 2.5. Okay, so what if I started off with my middle is 2, and here my middle equals 5. And let's say I want to get these closer, so I now move these. So I move this to the right and move this to the left. So now my middle becomes 3, and here my middle becomes 4, and then they end. And we're done. And then here I have these two values. And then I can do sort of a Yeah, so on an even, this sounds fine, right? On an even, this sounds fine. Let's do like 7, 10, 13, 14, and like 5, 8, 11, 12. So my median here equals 10, and my median here equals 8. And then, oh my goodness, Max, relax. We want to get these closer, so 10 needs to go down, 8 needs to go up. So I'm going to go to 7, and this one's going to go to 11. But that's not good. So this locks out at 7. And here I have 11 and 12. Yeah. So locks out at 7. This is low. Okay, so that idea doesn't work. Interesting. Thanks. Stop. Hey, relax. Hey, stop. Hey, stop. Sorry. Kind of blanking out. Tired right now. Apologies about that. Let's see. Hey, relax, relax. Hey, stop chewing on my cord, man. Hey, chill out. Ugh. Hey. I don't even want to try this one. I'm not gonna lie. I'm looking at this one. This is kind of cooking me. It's kind of frying me right now. I don't know. I give up. I'm trying to answer this math, but it's confusing me because this is saying the maximum is less than. This is saying it's greater than. Yeah. No.
Hey everyone, welcome back, and let's write some more neat code today. So today let's solve a pretty difficult problem, median of two sorted arrays. So we're given two arrays, nums1 and nums2, that are already in sorted order, but they could be of different sizes, m and n, and we want to return the median of both of the arrays when they have been put together and sorted. So not individually, but we want to put them together and then find the median of both of them. And not only that, but we want to do it efficiently. So log of m plus n worst case, right? So one example, we can see one array could be 1, 3, another array could be 2. And in this case, when you put the two arrays together, it's pretty obvious that 2 is the median, that the median is the middle value. Now we know that there are other examples where we might have an even number of total elements, 1, 2, 3, 4. When you put those together, we get 1, 2, 3, 4. In this case, we have two numbers that are in the middle, 2 and 3. So what do? We can just take the average of these two. And we know the average is 2.5. But both of these examples used a merged array. But we know if we actually merge two arrays together, like 1, 2, and 3, 4, the worst case is actually big O n plus m. And that's not a log. So we know in most cases when people want a log algorithm, you need binary search, and that's exactly what I'm going to show you right now, how to solve this problem with binary search. So let's say we are given a different example. Let's call this array B, and let's call this array A. So we know we can merge these two arrays, right? And then the median is obvious. But what exactly is a median? Well, it's the middle value, right? In this case, this is the middle value, and we know that because we know to the left of it, there are 6 elements, and to the right of it, there are 6 elements. So in this case, we have an array of 13 elements, and this happens to be the middle. The left partition of 6 elements is the same size as the right partition of 6 elements. So what we're doing is partitioning the array into 2 equal halves roughly, right? Because we know there's an odd case and an even case. Now let's just take hypothetically this 8 doesn't exist. Then in reality we have 12 elements. So we take the left partition to be 6 elements and the right partition to be 6 elements. So in that case we know we can take the 2 middlemost elements, or in other words the rightmost value in our left partition and the leftmost value in our right partition, and take the average. So add them together and divide by 2. We know that's going to be 3.5. So how can we simulate that without actually merging these two arrays? How can we simulate that with just the original arrays, which are still in sorted order, right? Luckily for us, they are given in sorted order. So keep in mind that the total number of elements we have in this case is 13, and half the number of elements we have is roughly 6. I'm going to round down in this case. And when we talk about partitioning, we want our left partition to be roughly equal to half. So when we partition this, we want the left to be roughly 6. So the most intuitive way to do this is let's get half of the elements of, let's say, A, right? So I'm going to have a left pointer initialized here, and I'm going to have a right pointer initialized here, and I'm going to find the middle. So we know this is index 0, this is index 4. I add them together and average. So we know that the middle is going to be 2, right? So what are we actually going to do? So this is going to be our middle value, right? And basically what that means is our left partition is going to include that. So far, our left partition initially is going to be like this. Now, obviously, we can increase it by adding an element. We can also decrease it by removing an element. But initially, let's have our left partition have 3 values in it. So it has 3 values. Great. Now, can we repeat that same process up here? Well, the good thing is we don't actually need to, because look, in this case, if we do that, we're going to get 4, and we can basically, if we want, we can run binary search up here too, but is that even necessary? Because look at this, half our elements are 6. So really what we can do is say half minus 3 over here is going to be equal to 3. So if we run binary search on just this bottom array, we can compute the size of the left partition for the second array, right? We can just compute it using our half value. And since we know 6 minus 3 is 3, we know initially we can say that the left partition of this is going to be 3 as well. We don't even need to keep a left and right pointer for this array. So these two subarrays make up our left partition. Now my question is, how do we know if we found the correct left partition or not? Well, we want them to be in order, right? So notice how we already know that this 3 is going to be less than or equal to the element that comes after it. That's what sorted order means. And we already know this value is going to be less than or equal to the value to the right of it, because this is also in sorted order. But we want to make sure that the left partition is less than or equal to every element in the right partition, and this is our right partition. So how can we determine that? Well, one thing we can ask is the rightmost element in this part of the partition less than or equal to this value? And in this case it is. We also want to ask, is this value less than or equal to the leftmost value in this part of the partition, in the right partition? Is it less than or equal to that? In this case, it is. And what this tells us is that our left partition has been done correctly. And if it's not clear enough, let me just write it out again. So remember, if we merge these two arrays, this is what it's going to look like. And our left partition is going to be this, right? We have 13 elements. This is our left partition. And we can say that this is our right partition, but since it's odd, we can add that extra element. And you can see that that's exactly what we found here, right? Okay, so we know we found the left partition correctly, right? So the left is going to be this 6 element, but how do we find that middle value? Well, in this case, either of these two is a 4, so either of them is going to be the median, right? We have 2 4s, either of them could be the median. But hypothetically, let's say one of these was a 5, so let's say maybe in the top we had a 5, so this would be a 5. How would we find the median in that case? Well, from these two values, right, we know one of them has to be the median. What we would do is take the minimum of both of them. So we take the minimum of the leftmost values in both partitions. So the min...
Oh, I'm not gonna lie. I got to go. It is late. And I have to get stuff prepared. So I'm gonna have to just work on this tomorrow. Sorry about the video being short, but I gotta go. Thank you for watching. I will see y'all tomorrow.